The lesson that we will have today is about the review of thermal sciences. This is presented by De Leon, Juan Gabriel, Evangelista, Revan Steven, and Kato, Gyoji. This presentation will cover thermodynamics. In thermodynamics, we have heat and other forms of energy, specific heats of gases, liquids, and solids, energy transfer, the first law of thermodynamics, energy balance for closed systems, energy balance for steady flow systems, saturation temperature and saturation pressure. Next is heat transfer. In heat transfer, we have conduction heat transfer, thermal conductivity, convection heat transfer, and radiation heat transfer. We also have fluid mechanics, which has viscosity and pressure drop in fluid flow in pipes. We also have thermochemistry, which includes fuels and combustion, theoretical and actual combustion processes, enthalpy of formation and enthalpy of combustion, and first law analysis of reacting systems. We also have heat engines and power plants, which has thermal efficiency and overall plant efficiency. Lastly, we have refrigerators and heat pumps. So, what is thermal sciences? Energy and its transfer, transport, and conversion are the focus of physical sciences. Thermal fluid sciences, or simply thermal sciences, are the terms used to describe the study of energy. Thermodynamics, heat transfer, and fluid mechanics are the traditional subcategories of the thermal fluid sciences. The analysis of renewable energy systems includes a thorough understanding of energy conversion processes, energy transformations, and methods for determining the efficiency of energy producing and consuming systems. This goes through the basics to provide a solid and usable foundation for the study of thermodynamics, heat transfer, fluid mechanics, thermochemistry, power plants, and refrigeration systems for renewable energy. Now we go to thermodynamics. Thermodynamics can be defined as the science of energy and also the energy that can be viewed as the ability to cause changes. Thermodynamics is derived from the Greek word therme, which means heat, and dynamis, which means power, and it best describes the early attempts to convert heat into power. Today, the same name is broadly interpreted to include all aspects of energy and energy transformations, including power generation, refrigeration, and relationships among the properties of matter. The first law of thermodynamics is simply an expression of the conversion of energy principle, and it asserts that the energy is a thermodynamic property. The second law of thermodynamics asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. Third law of thermodynamics tells us that entropy of a system approaches a constant value as the temperature approaches absolute zero. One of the most fundamental laws of nature is the conservation of energy principle. It simply states that during an interaction, energy can change from one form to another, but the total amount of energy remains constant. That is, energy cannot be created or destroyed. Next is heat and other forms of energy. Thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, and nuclear energy are all kinds of energy, and their aggregate is the total energy E, or E on a unit mass basis of a system. Microscopic energy refers to the types of energy associated with a system's molecular structure and degree of molecular activity. The internal energy of a system, indicated by U, is the sum of all microscopic types of energy. The international unit of energy is joule or kilojoule. Another well-known unit of energy is the calorie, where 1 calorie is equal to 4.1868 joules, which is defined as the energy needed to raise the temperature of 1 gram of water at 14.5 by 1 degrees Celsius. In the English system, the unit of energy is the British Thermal Unit, or BTU. 1 BTU is equals to 1.055056 kilojoules. The portion of the internal energy of a system associated with the kinetic energy of the molecules is called sensible energy or sensible heat. The temperature influences the average velocity and degree of activity of the molecules. As a result, at higher temperatures, the molecules have more kinetic energy and the system has more internal energy. The internal energy associated with the atomic bonds in a molecule is called chemical or bond energy. These are the forces that hold molecules together, and they are strongest in solids and lowest in gases. When enough energy is applied to the molecules in a solid or liquid, these molecular forces are overcome, and the system transforms into a gas. This is a phase shift process, and a system in the gas phase has a higher internal energy level than one in the liquid phase. The internal energy associated with the system phase is known as latent heat or latent energy. In the analysis of systems that involve fluid flow, we frequently encounter a combination of properties, internal energy U, and flow energy PV. For the sake of simplicity and convenience, this combination is defined as the specific enthalpy H or just enthalpy. Enthalpy can be denoted as enthalpy H is equals to internal energy U plus PV, where the term PV represents the flow energy of the fluid, also can be called as the flow work. Next is the specific heats of gases, liquids, and solids. An ideal gas is defined as a gas that obeys the relation PV is equals to RT or P is equals to rho times RT, where P is the absolute pressure, V is the specific volume, T is the thermodynamic or absolute temperature, rho is the density, and R is the gas constant. It has been experimentally observed that the ideal gas relation given above closely approximates the PVT behavior of real gases at low densities. The density of a gas reduces at low pressures and high temperatures, and the gas acts like an ideal gas. Many known gases, such as air, nitrogen, oxygen, hydrogen, helium, argon, neon, and krypton, and even heavier gases, such as carbon dioxide, can be handled as ideal gases with low inaccuracy in the range of practical concern, often less than 1%. Dense gases like water vapor in steam, power plants, and refrigerant vapor in refrigerators, on the other hand, should not necessarily be classified as ideal gases because they are usually near saturation. The internal energy U represents the microscopic energy of a non-flowing fluid, whereas enthalpy H represents the microscopic energy of a flowing fluid. Specific heat is defined as the energy required to raise the temperature of a unit mass of substance by 1 degree. This energy is mostly determined by how the operation is carried out. Specific heats at constant volume Cv and specific heat at constant pressure Cp are the two types of specific heats that we are normally interested in. The energy required to increase the temperature of a unit mass of a substance by 1 degree while keeping the volume constant is known as specific heat at constant volume Cv. The specific heat at constant pressure Cp is the energy required to achieve the same when the pressure is held constant. For ideal gases, these two specific heats are related to each other by Cp is equals to Cv plus R. Because the system is permitted to grow at constant pressure, the energy required for this expansion work must also be given to the system. A common unit for specific heat is kilojoule per kilogram degree Celsius or kilojoule per kilogram Kelvin. Also, 1 kilojoule per kilogram degree Celsius is equals to 1 joule per gram degree Celsius, and 1 kilojoule per kilogram Kelvin is also equals to 1 joule per grams Kelvin. For English system, 1 BTU per pounds mass degrees Fahrenheit is equals to 1 BTU per pounds Rankine. In general, a substance's specific heat is determined by two separate quantities, which is temperature and pressure. However, for an ideal gas, they depend on temperature only. Because all real gases approach perfect gas behavior at low pressures, their specific heats are solely determined by temperature. The differential changes in the internal energy U and enthalpy H of an ideal gas can be expressed in terms of the specific heats as the derivative of internal energy U is equals to Cv times the derivative of temperature, and the derivative of enthalpy H is equals to Cp times the derivative of temperature. The finite changes in the internal energy and enthalpy of an ideal gas during a process can be expressed approximately by using specific heat values at the average temperature as the derivative of internal energy U is equals to Cv average times the derivative of temperature, and the derivative of enthalpy H is equals to Cp average times the derivative of temperature. Or the derivative of internal energy U is equals to mass times the Cv average and times the derivative of temperature, and the derivative of H enthalpy is equals to mass times that Cp average times the derivative of temperature. A substance whose specific volume or density does not change with temperature or pressure is called an incompressible substance. The specific volumes of solids and liquids essentially remain constant during a process, and thus they can be approximated as incompressible substances without sacrificing much in accuracy. The specific heats of incompressible substances depend on temperature only. Therefore, the change in the internal energy of solids and liquids can be expressed as the derivative of energy U is equals to mass times the C average times the derivative of temperature, where C average is the average specific heat evaluated at the average temperature. Note that the internal energy change of the systems that remain in a single phase, liquid, solid, or gas, during the process can be determined very easily using average specific heats. Next is energy transfer. Two methods can transmit energy to or from a given mass: heat transfer Q and work W. When the driving force of an energy exchange is a temperature differential, it is called heat transfer. Otherwise, it is work. Work interactions are represented by a rising piston, a rotating shaft, and an electrical wire crossing system boundaries. Power is the amount of work done per unit of time and is represented by the letter W. The unit of power is kilowatts or HP, where 1 HP horsepower is equal to 0.746 kilowatts. When the rate of heat transfer is available, then the total amount of heat transfer Q during a time interval can be determined from amount of heat transfer Q is equal to the integral of the rate of heat transfer with respect to time, provided that the variation of rate of heat transfer with time is known. For the special case of rate of heat transfer is constant, the equation above reduces to amount of heat transfer Q is equal to the rate of heat transfer time to the change in time. Next is the first law of thermodynamics. The first law of thermodynamics, also known as the conservation of energy principle, states that energy can neither be created nor be destroyed during a process. It can only change forms. As a result, during a process, every ounce of energy must be accounted for. For any system undergoing any process, the conservation of energy principle can be expressed as follows. The net change, increase or decrease, in the total energy of the system during a process is equal to the difference between the total energy entering and the total energy leaving the system during that process. Noting that energy can be transferred to or from a system by heat, work, and mass flow, and that the total energy of a simple compressible system consists of internal, kinetic, and potential energies, the energy balance for any system undergoing any process can be expressed as energy in minus energy out is equal to the total change of energy in the system. In the absence of significant electric, magnetic, motion, gravity, and surface tension effects, the change in the total energy of a system during a process is simply the change in its internal energy. That is, derivative of energy in the system is equal to the derivative of internal energy of the system. Energy balance can be written in the rate form as energy in minus energy out is equal to the derivative of energy in the system divided by the derivative of time. Energy is a property, and the value of a property does not change unless the state of the system changes. Therefore, the energy change of a system is zero if the state of the system does not change during that process. That is, the process is steady. The energy balance in this case reduces to E in is equals to E out. In steady operation, the rate of energy transferred to a system is equal to the rate of energy transferred from the system. Next is the energy balance for closed systems. A closed system consists of a fixed mass. The total energy E for most systems encountered in practice consists of the internal energy U. This is especially the case for stationary systems since they do not involve any changes in their velocity or elevation during a process. The energy balance relation in that case reduces to, if it is a stationary closed system, E in minus E out is equals to the change of internal energy equals to mass times the constant volume times the change in temperature, where we express the internal energy change in terms of mass m, specific heat at constant volume Cv, and the temperature change of the system. When the system involves heat transfer only and no work interactions across its boundary, the energy balance relation further reduces to when stationary closed system that has no work is equals to Q is equals to mass times Cv times the change in temperature, where Q is the net amount of heat transferred to or from the system. This is the form of the energy balance relation we use most often when dealing with a fixed mass. Energy balance for steady flow system. The amount of mass flowing through a cross-section of a flow device per unit time is called the mass flow rate and is denoted by m. A fluid may flow in and out of a controlled volume through pipes or ducts. The mass flow rate of a fluid flowing in a pipe or duct is proportional to the cross-sectional area of the pipe or duct, the density ρ, and the velocity v of the fluid. The flow of a fluid through a pipe or duct can often be approximated to be one-dimensional. That is, the properties can be assumed to vary in one direction only. Under the one-dimensional flow approximation, the mass flow rate of a fluid flowing in a pipe or duct can be expressed as mass flow rate m is equal to density ρ times velocity v times cross-sectional area A. The volume of a fluid flowing through a pipe or duct per unit time is called the volume flow rate v and is expressed as volume flow rate v is equals to velocity times cross-sectional area A and also equals to mass flow rate m divided by density ρ. Note that the mass flow rate of a fluid through a pipe or duct remains constant during steady flow. This is not the case for the volume flow rate, however, unless the density of the fluid remains constant. In the absence of any work interactions, the change in the energy content of a closed system is equal to the net heat transfer. The mass flow rate of a fluid at a cross-section is equal to the product of the fluid density, average fluid density, and the cross-sectional area. Under steady conditions, the net rate of energy transferred to a fluid in a controlled volume is equal to the rate of increase in the energy of the fluid stream flowing through the controlled volume. Next is the saturation temperature and saturation pressure. Water starts to boil at 100 degrees Celsius. Strictly speaking, the statement water boils at 100 degrees Celsius is incorrect. The correct statement is water boils at 100 degrees Celsius at 1 atmospheric pressure. At 500 kilopascal pressure, water boils at 151.8 degrees Celsius. That is, the temperature at which water starts boiling depends on the pressure. Therefore, if the pressure is fixed, so is the boiling temperature. At a given pressure, the temperature at which a pure substance changes phase is called the saturation temperature. Likewise, at a given temperature, the pressure at which a pure substance changes phase is called the saturation pressure. At a pressure of 101.3 kilopascal, saturation temperature is 100 degrees Celsius. Conversely, at a temperature of 100 degrees Celsius, saturation pressure is 101.3 kilopascal. This table indicates that the pressure of water changing phase, boiling or condensing, at 25 degrees Celsius must be at 3.17 kilopascal, and the pressure of water must be maintained at 3,976 kilopascal or about 40 atm to have it boil at 250 degrees Celsius. Also, water can be frozen by dropping its pressure below 0.61 kilopascal. During a phase change process, pressure and temperature are obviously dependent properties, and there is a definite relation between them. A plot of saturation temperature versus saturation pressure, such as the one given for water in the figure, is called a liquid vapor saturation curve. A curve of this kind is the characteristic of all pure substances. The figure here shows that the saturation temperature increases with the saturation pressure. Thus, a substance at a higher pressure boils at higher temperatures. The atmospheric pressure, and thus the boiling temperature of water, decreases with elevation. Therefore, it takes longer to cook at higher altitudes than it does at sea level, unless a pressure cooker is used. For example, the standard atmospheric pressure at an elevation of 2,000 meters is 79.50 kilopascal, which corresponds to a boiling temperature of 93.3 degrees Celsius as opposed to the 100 degrees Celsius at sea level. For each 1,000 meters increase in elevation, the boiling temperature drops by a little over 3 degrees Celsius.
Heat transfer. Heat transfer is the science that deals with the rates of heat energy transfer. Heat is a form of energy that can be transferred from one system to another as a result of difference in temperatures of the two medium. Heat can travel from one place to another through several ways, such as conduction, convection, and radiation. In a conduction heat transfer, heat flows from a higher temperature object to a lower temperature one. As conduction can take place in solids, liquids, and gases, the transfer of energy differs. In gases and liquids, conduction takes place due to the collision and diffusion of molecules during their random motion, while in solid, it is due to the combination of vibration of the molecules in a lattice and the energy transport by free electrons. The rate of which heat conduction through a medium depends on the geometry of the medium, its thickness, the type of material, and as well as the temperature difference across the medium. One example of heat conduction is when we iron our clothes. Conduction takes place where the heat from the iron is conducted to the clothes. Conduction heat transfer can be expressed through this formula. Conduction heat transfer is equals to K times A times delta T over delta X, where K is the thermal conductivity of the material, A is the area, delta T is the temperature difference, and delta X is the length of the materials. This can also be expressed in differential form, which is also known as the Fourier's law of heat conduction. Thermal conductivity. Thermal conductivity can be defined as the rate at which heat is transferred by conducting through a unit of cross-section area of a material when a temperature gradient exists perpendicular to the area. A high number of thermal conductivity means that the material is a good heat conductor, and a low number means that the material is a poor heat conductor. Here is a table of several materials with their corresponding thermal conductivity. Convection heat transfer. Convection is a process by which heat is transferred by movement of heated fluids such as gas or liquids. Natural convection results from the tendency of most fluids to expand when heated, to become less dense, and to rise as a result of the increased buoyancy. Forced convection involves the transport of fluids by methods other than that resulting from variation of density with temperature. Movement of air by a fan or of water by a pump are examples of forced convection. Atmospheric convection currents can be set up by local heating effects such as solar radiation or contact with cold surface masses. Such convection currents primarily moves vertically and account for many atmospheric phenomena such as cloud and thunderstorms. Heat convection transfer can be expressed by the equation Heat convection heat transfer is equals to H, which is the heat transfer coefficient multiplied by A sub S, quantity T sub x minus T infinity. Radiation heat transfer. Radiation heat transfer is a process by which energy, in the form of electromagnetic radiation, is emitted by a heated surface in all directions and travels directly to its point of absorption at the speed of light. Radiation heat transfer does not require an intervening medium to carry it. The rate at which a body radiates or absorbs thermal radiation depends upon the nature of the source as well. Objects that are good emitters are also good absorbers. The maximum rate of radiation can be expressed as Q emit max is equals to Stefan Boltzmann constant multiplied by A sub S T raised to 4 sub S. Radiation emitted by black body at the same temperature is equals to Q emit is equals to emissivity times Stefan Boltzmann constant times A sub S T raised to 4 sub S. The table shows the emissivity of some materials at 300 K temperature. Another important radiation property of a surface is its absorptivity, A, which is the fraction of the radiation energy incident on a surface that is absorbed by the surface. Like emissivity, its value is in the range of more than 0 but less than 1. A black body absorbs the entire radiation incident on it. A black body is a perfect absorber, which its A is equals to 1 as it is also a perfect emitter. In general, both E and A of a surface depend on the temperature and the wavelength of the radiation. Kirchhoff's law of radiation states that the emissivity and the absorptivity of a surface at a given temperature and wavelength are equal. The rate at which a surface absorbs radiation can be expressed as Q absorbed is equals to absorptivity of the surface times Q incident. On a surface of emissivity and surface area at a thermodynamic temperature T completely enclosed by a much larger or black surface at a thermodynamic temperature separated by a gas such as air that does not intervene with radiation. The net rate of radiation heat transfer between these two surfaces can be expressed as Q rad is equals to emissivity times Stefan Boltzmann constant times A quantity thermodynamic temperature minus thermodynamic temperature separated by gas raised to 4. The total heat transfer rate to or from a surface by convection and radiation is expressed as fluid mechanics. Mechanics is a physical science that deals with both stationary and moving bodies under the influence of forces. Fluid mechanics is the science that deals with the behavior of fluids at rest, fluid static, and in motion, fluid dynamics, and its interaction to others. Subcategories for fluid mechanics includes hydrodynamics, gas dynamics, aerodynamics, and hydraulics. Viscosity. Viscosity is the resistance of fluid, liquid, or gas to a change in shape or movement of neighboring portions relative to one another. Viscosity denotes opposition to flow. The viscosities of different fluids differ by several orders of magnitude. It is more difficult to move an object in a higher viscosity fluid, such as engine oil, than it is in a lower viscosity fluid, such as water. The viscosity of liquids decreases rapidly with an increase in temperature, and the viscosity of gases increase with an increase of temperature, which is shown by the diagram at the right. There are two types of fluids: Newtonian fluids, liquids that obey Newton's law of viscosity, and non-Newtonian fluids that does not obey Newton's law of viscosity. Newton's law. Newton's law can be expressed as shear stress is equals to coefficient of viscosity multiplied by the shear rate. The unit of viscosity is equals to kilogram per meter second or Newton second per meter squared or Pascal second. Pressure drop in fluid flows in pipes. Pressure loss is the difference in total pressure between 2 points in a fluid carrying network. Head loss is a measurement of the energy dissipated in a fluid system due to friction along the length of a pipe or hydraulic system, and those due to fittings, bulbs, and other system structures. Pressure loss can be expressed as pressure loss equals to friction factor times pipe length over diameter times dynamic pressure. Head loss is equals to pressure loss over density times gravitational acceleration. For a developed laminar flow in a round pipe, the friction factor is F is equals to 64 over Reynolds. For laminar flow in a horizontal pipe, the pressure difference between the two ends is equals to 32 times dynamic viscosity times length of pipe times volumetric flow rate all over diameter squared, which is Possel's law. For non-circular pipes, diameter D will be hydraulic diameter. Hydraulic diameter is equals to 4 times A times T times P, where P is the wetted perimeter. For fully developed turbulent flow, friction depends on Reynolds and relative roughness. Friction Friction factor in turbulent flow can be denoted as 1 over square root of F is equals to negative 2 log quantity relative roughness over 3 times 3.7 plus 2.51 over Reynolds times square root of F, which is also known as the Colebrook equation. It is only used in turbulent pipe flow. To calculate the power required to overcome pressure loss, we can use the equation below, where B is the volume flow rate and M is the mass flow rate.
Thermochemistry. In this section, we review basic concepts and principles of thermochemistry, which is thermodynamic study of chemical reactions, particularly combustion reaction. Fuels and combustion. Fuels. Any material that can be burned to release thermal energy is called a fuel. Most familiar fuels consist primarily of hydrogen and carbon. Combustion. A chemical reaction during which a fuel is oxidized and a large quantity of energy is released is called combustion. The oxidizer most often used in combustion processes is air, as it is free and readily available. During a combustion process, the components that exist before the reactions are called reactants, and the components that exist after the reactions are called products. Bringing a fuel into intimate contact with oxygen is not sufficient to start a combustion process. The fuel must be brought above its ignition temperature to start the combustion. Combustion. The minimum ignition temperature of various substances in atmospheric air are approximately 260 Celsius for gasoline, 400 Celsius for carbon, 580 Celsius for hydrogen, 610 Celsius for carbon monoxide, and 630 for methane. Moreover, the proportions of the fuel and air must be in the proper range for combustion to begin. A frequently used quantity in the analysis of combustion processes to quantify the amounts of fuel and air is the air-fuel ratio, AF. It is usually expressed on a mass basis and is defined as the ratio of the mass of air to the mass of fuel for combustion process, which is shown in the screen. The mass of m of a substance is related to the number of moles n through the relation m is equal to nm, and where m is the molar mass. Theoretical and actual combustion. It is often instructive to study the combustion of a fuel by assuming that the combustion is complete. A combustion process is complete if all the carbon in the fuel burns to CO2, and all the hydrogen burns to H2O, and all the sulfur, if any, burns to SO2. That is, all the combustible components of a fuel are burned to completion during a complete combustion process. Conversely, the combustion process is incomplete if the combustion products contain any unburned fuel or components such as C, H2, CO, or OH. Reason for incomplete combustion: insufficient oxygen. Occurs when more oxygen is present in the combustion chamber than is needed for complete combustion. Dissociation process, considered as the disintegration of combustion produce at high temperature. The minimum amount of air needed for the complete combustion of a fuel is called the stoichiometric or theoretical air. Thus, when a fuel is completely burned with theoretical air, no uncombined oxygen is present in the product gases. The theoretical air is also referred to as the chemical correct amount of air, or 100% theoretical air. A combustion process with less than the theoretical air is bound to be incomplete. The amount of air in excess of the theoretical air is called excess air. The amount of excess air is usually expressed in terms of stoichiometric air as percent excess air or percent theoretical air. Amounts of air less than the stoichiometric amount are called deficiency of air and are often expressed as percent deficiency of air. For example, 90% theoretical air is equivalent to 10% deficiency of air. The amount of air used in combustion processes is also expressed in terms of the equivalence ratio, which is the ratio of the actual fuel air ratio to the stoichiometric fuel air ratio. Enthalpy of formation and enthalpy of combustion. During a chemical reaction, some chemical bonds that bind the atoms into molecules are broken, and new ones are formed. The chemical energy associated with these bonds in general is different for the reactants and the products. Therefore, a process that involves chemical reaction involves changes in chemical energies, which must be accounted for in an energy balance. Assuming the atoms of each reactant remain intact and disregarding any changes in kinetic and potential energies, the energy change of a system during a chemical reaction is due to a change in state and a change in chemical composition. That is, delta E system is equal to delta E state plus delta E chemical composition. The chosen reference state is 25 Celsius or 77 Fahrenheit and 1 atm, which is known as the standard reference state. For combustion process, the enthalpy of reaction is usually referred to as the enthalpy of combustion h lowercase c, which represents the amount of heat released during a steady flow combustion process. When 1 kilomole or 1 kg of fuel is burned completely at a specified temperature and pressure, it is expressed as HR is equal to HC is equal to H product minus H react. The enthalpy of combustion is obviously a very useful property for analyzing the combustion process of fuels. However, there are so many different fuels and fuel mixtures that it's not practical to list H lowercase c values for all possible cases. The enthalpy of formation HOF, which can be viewed as the enthalpy of a substance at a specified state due to its chemical composition. Another term commonly used in conjunction with the combustion of fuels is the heating value of the fuel, which is defined as the amount of heat released when a fuel is burned completely in a steady flow process, and the products are returned to the state of reactants. Heating value is equal to absolute value of Hc. The heating value is called the higher heating value, HHV, when the H2O in the products is in the liquid form, and it's called the lower heating value, LHV, when the H2O in the product is in the vapor form. M is the mass of water. HHV is equal to LHV plus MH of FG H2O. First law analysis of reacting systems. Before writing the energy balance relation, we need to express the enthalpy of a component in a form suitable for a use for reacting systems. That is, we need to express the enthalpy such that it is relative to the standard reference state and the chemical energy term appears explicitly. When expressed properly, the enthalpy term should reduce the enthalpy of formation at the standard reference state. With this in mind, we express the enthalpy of a component on a unit mole basis as the formula shown below, where the term in the parentheses represents the sensible enthalpy relative to the standard reference state, which is the difference between the sensible enthalpy at the specified state and the sensible enthalpy at the standard reference state of 25 Celsius and 1 atm. When the changes in kinetic and potential energies are negligible, the steady flow energy balance relation E in is equal to E out can be expressed for a chemically reacting steady flow system more explicitly as the formula shown, where NP and NR represent the molar flow rates of the product P and the reactant R respectively. In a combustion analysis, it is more convenient to work with quantities expressed per mole of fuel. Such a relation is obtained by dividing each term of the equation shown before by the molar flow rate of the fuel yielding, where capital N, P, and NR represent the number of moles of the reactant R and the product P, respectively, per mole of fuel. A combustion chamber normally involves heat output but no heat input. Then the energy balance for a typical steady flow combustion process becomes like the formula shown. Heat engines and power plants, thermal efficiency and overall plant efficiency. Heat engines characteristics. First, they receive heat from a high temperature source, like solar energy, oil furnace, nuclear reactor, etc. They convert part of this heat to work, usually in the form of a rotating shaft. Third, they reject the remaining waste heat to a low temperature sink. Fourth, they operate on a cycle. As you can see on the diagram shown, which shows the characteristics of heat engines. Steam power plant. The formula is shown where W net out is equal to W out minus W in. The network can also be determined from the heat transfer data alone, where W net out is equal to Q in minus Q out. Q in is equal to amount of heat supplied to a steam in boiler from a high temperature source or furnace. Q out is equal to amount of heat rejected from the steam in condenser to a low temperature sink, the atmosphere, a river, etc. W out, amount of work delivered by a steam as it expands in turbine. W in, amount of work required to compress water to boiler pressure. Thermal efficiency and network output. W net out is equal to Q in minus Q out. Thermal efficiency N is equal to network output over total heat input is equal to W net out over Q in. Thermal efficiency cannot cycle. The most efficient heat engine cycle is referred to as Carnot cycle, which consists of totally reversible process. Nth Carnot is equal to 1 minus TL over TH, where TL is equal to low temperature, TH is equal to high temperature. Overall plant efficiency. Overall plant efficiency based on the total energy of the fuel consumed in the plant. End plant is equal to network output over total amount of heat input by fuel is equal to W net out over M fuel multiplied by HV fuel, where W net out is equal to network output of the plant. M fuel is equal to network output of the plant kg. HV fuel is equal to heating value of the fuel HK. It may also be expressed on a rate basis as where N plant is equal to net power output over total rate of heat input by fuel is equal to W net out over M fuel times HV fuel, where W net out is equal to network output of the plant. M fuel is equal to mass rate of fuel consumed, and H fuel is still heating value of the fuel. Refrigerator and heat pumps. Refrigerator is a device used to keep a space cool and is called an air conditioner when indoor spaces of a building is kept at a lower temperature than the ambient air in the summer. Refrigerator and heat pumps. Refrigerator are cyclic devices, and the working fluids are used in the refrigeration cycles are called refrigerants. Here, QL is the magnitude of the heat removed from the refrigerated space at temperature TL. QH is the magnitude of the heat rejected to the warm space at the temperature TH, and the W net in is the net work input to the refrigerator. Note that QL and QH represent magnitudes and thus the positive quantities. As you can see here in the diagram on the side. Another device that transfers heat from a low temperature medium to a high temperature one is the heat pump, like on the figure on the right. Refrigerators and heat pumps are essentially the same devices. They differ in their objectives only. The objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. Discharging this heat to a higher temperature medium is merely a necessary part of their operation, not the purpose. The performance of refrigerator and heat pumps is expressed in the terms of coefficient of performance, COP, defined as COPR is equal to cooling effect over work input is equal to QL over W net in, COP HP is equal to heating effect over work input is equal to QH over W net in, or in rate form, COPR is equal to QL over W net in, and COP HP is equal to QH is over W net in. Notice that both COPR and COP HP can be greater than 1. A comparison of the two equations shown before reveals that COP HP is equal to COPR plus 1. For fixed values of QL and QH, this relation implies that COP HP is greater than equal 1 since COPR is a positive quantity. That is, a heat pump functions at worst as a resistance heater, supplying as much energy to the house as it consumes. The cooling capacity of a refrigerator system, that is, the rate of heat removal from the refrigerated space, is often expressed in terms of tons of refrigeration. The capacity of a refrigeration system that can freeze 1 ton of liquid water at 0 Celsius into ice at 0 Celsius in 24 hours is said to be 1 ton. 1 ton of refrigeration is equivalent to 211 kilojoules per min, or 200 BTU per minute, or 12,000 BTU per hour. The cooling load of a typical 200 M2 residence is in the 3 ton or 10 kilowatt range. And that is all. Thank you.